Hi, my name is Mel Halkershoven and I'm going to talk about IP addressing. This basic topic is just introducing you to connecting computers to a network, what's required to be able to communicate between computers, and this is useful for anyone who wants to set up IP cameras. So you might have security cameras that you're configuring. For most computers on local networks, small home networks, this is done automatically for you by the router. However, it's important for you for troubleshooting to actually know and understand how this works. So let's get into it. Basic introduction, what is an IP address? We're just going to talk about this structure, what it means. We go into binary coding just so you can understand what's actually happening behind the scenes. Not too difficult, just the introduction. IP address classes, the private IP addresses that are available to you to use on a private network, how to select an IP address for computers to communicate in a network, subnet masks and what they mean. The CIDR notation, it's an alternative way of writing the IP address. You just need to recognize and understand what that means. Very, very briefly going to mention supernetting and subnetting, and then what the meaning is of IPv6. So what is an IP address? To use an analogy, when we write a letter and you send the letter to a friend or someone you know or a business, there's a certain structure for how you must write that letter. So as you can see here in this letter, we've got TAFE SA Regency Park. That's who you're sending it to. That's their name. So this is expected on every letter that you send. On the next line, you've actually got the street, the number and the street. And then on the last line, we've got the suburb, the state, and the postcode. If you didn't have all that information on there, the letter wouldn't actually reach its destination. And as a final point, see how you have to put the stamp on the letter as well. Without this stamp, the post office is not going to deliver your letter. So think of this as part of your protocol. When you send the letter, all these things are required as part of the protocol. And when we look at IP addresses, there are different rules that are required. So here we've got the envelope, we have an IP address and a subnet mask which is underneath. We're going to go a bit more into detail about what these mean. Okay, the IPv4 address structure. I must point out here that we're only talking about IPv4 here. There is IPv6 coming up in the future. Everything's totally different, these roles. So just remember it's IPv4. The address is actually 4 octets separated by a dot. Okay, so you'll see here you've got 4 numbers, 192.168.1.1. Okay, each one of those numbers in between the dots is called an octet. And all these IP addresses, the computer behind the scenes actually sees these numbers that we use as binary. It converts them into a binary, which is a series of ones and zeros. So you can see here I've actually converted that IP address into binary. And you can see there that the first binary number is made up of 8 bits. So if you actually count the number of bits there, which is each digit in binary, that actually makes up 8 of them. That's why we call it 1 octet. Okay, and finally, because of this addressing system, that means that we have that number over 4 billion IP addresses available in total. It's a finite number, and that's actually 2 to the power of 32. Now, that seems like a lot. However, when IPv4 was first invented, we thought 4 billion would more than exceed the number of computers we would ever need. Of course, that was back in the day when computers weren't as popular as they are now, and now every home pretty much has a computer. And also, if you consider all the mobile devices and iPads, so in one household, people can have anywhere from 2 to 10 different devices connecting to the internet, such as televisions as well. Maybe one day we'll have microwave ovens as well connecting to the internet. That's something I'm looking forward to. So let's go into binary. Now, if you have a look at the left-hand column there, this is the decimal system that we're used to counting in. So we go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And once we reach 9, we've got no more numbers. So we actually go back to 0 and we add a 1 in front of it, which gives us 10. Now, we're all very familiar with counting in this, what we call the base 10 decimal system. Binary only has a base 2 system. So if you consider a 0 in electronics, a 0 would be electricity off, and a 1 is with the electricity on, just in simple terms. So binary is very useful for computers for this reason, because it's simply power on and off. But it's a little bit harder for humans to actually count in. But here you can see I've highlighted in red where we've reached the maximum number. So here we've reached 1, and then we go back to 0, and then we increment the next number. So the same as in the decimal system, but where we had 9 digits, when you reach 9 and then you increment the second column, in binary you only get to 1 before you go back to 0 and increment. So that's really important to remember, that the counting system really isn't that much different. It's just that your base that you count up to has changed. If we now look at this, so there's the 1. If we actually have a look at just the location, so if we've got just 1 on the right hand side, the value equals 1. But now let's have a look at when there's just a 1 in the second location from the right. See how we got 1, 0, and that equals 2. Now we go to the third spot. See how we have 1, 0, 0. Now we've doubled from 2 and we have 4. And something interesting happens when we look at keep looking at just that fourth location. We now have 8. We've doubled 4 to 8. Let's actually have a look at this in another table that I've got here. Remember, we're focusing just on turning on that 1. And you'll see on the decimal equivalent doubles each time. We have 0, 1, 2, 4. We double 4 to get 8, 16, 32, 64, and so on. This is important because you may be familiar with a lot of these numbers, because everything that you buy to do with a computer, which is hard drives, memory sticks, RAM for your computer, these have always been available in one of these values. And this is why. This is where it comes from. Someone didn't just decide to make available 16 gig of a USB stick. It's that value because of our binary base system, and because the computer is actually based on electronics. So this makes it a little bit easier when we go to actually calculating and working out our IP addressing, because we know we're familiar with these numbers. Okay, we're familiar with these values. Now to go basically, this is another way of representing it. So if we consider now in our IP address, we've got 8 bits here, which is represents one of our octets in our IP address. So we're looking at the values here as they go from right to left. So if we put a 1 in any of these locations, then that means that's added on in the value. I'll explain, this is a bit confusing, I'll explain what I mean. We're going to convert this number into decimal. So to convert this into decimal, we've got a 1 and a 1, and then the rest of the values are 0. So we consider them turned off. To add this up and turn it into a decimal number, we simply add the locations where there's a value of 1. So you can see from our graph at the top, we can determine what those values would be, and then we turn them on in the bottom where we're doing our calculation. So 128 plus 164, and the rest are 0. So 1 plus 0 plus 0 plus 0. And that equals 192. So this is, now you don't have to know this for any of your tests. I don't expect you to memorize this. You're just learning to understand how we actually arrive at these values. Now your textbook talks about powers and 2 to the power 4 and whatnot. It's very, very confusing. So forget about that complicated way of calculating and turning binary numbers into decimal. This is the easy way. Okay, you just find the value of that location, the bit that you're turning on. Say here, if we put a 1 in this location, we would add on a 2 down here. So let's go to another example. So here we have another IP address. So in the first location, we're going to be turning on the 128. Okay, then there's a 0, so we don't turn that one on. This one here, so we're going to turn on the 32, 0, 0, 0, 0, and the 1. So we're going to turn on the 1 here. So this is what it's going to look like. 128 plus 32 plus 1, because all the rest are zeros. And I worked that out for you. It's 161. Okay, if we had all of the bits turned off, so if we have all zeros, we're going to get 0. So this is the lowest possible number that we can have in our IP address. Okay, if we turn them all on, we're going to have all 1s, and if you add them all together, 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1, you're going to get 255. So that's the highest number that can ever exist in an IP address, so in each of your octets. Okay, so this is the lowest IP address you can possibly have, and there's the highest, 255.255.255.255. Okay, so now that we know the range, we're going from 1 to 255, we're going to have a look at the IP address classes. Now what we're talking about here, so you can see I've got the address classes A, B, C, D and E in the first column. In the second column, I've specified the first octet range. So that first octet represents the first, before the first dot in your IP address. And anything that's before that first dot that's from 1 to 127 is called a Class A address. Okay, anything from in that first octet from 128 to 191 is a Class B address, and so on. So if you see there's a Class C, D and E. Now the Class A addresses, those addresses give you 126 networks. You might say, okay, but it says 127. You've got 1 to 127. That's because 127 is a special IP address range just for diagnostic testing on your computer. That's the local host. So you might be familiar with 127.0.0.1. If you're not, you'll come across it at some stage in your practicals and in your studies. So we wipe that one out. That one's not usable on the internet at all. Now the Class B addresses is from 128 to 191, and those are broken up a bit more to give us over 16,000 networks. And out of the Class C addresses, these are broken up into smaller ones. I'll explain how that's done later. And that gives you over 2 million networks. But in a Class C, you can only have 254 computers per network. So they're meant to be much smaller networks. And then the Class D is reserved for multicasting, so you can never use an IP address from that starts with anything above 224. And Class E is experimental use only. Now what happened when the classes were first designed? they figured that they had heaps of addresses, or something new would come along before they would run out. And at the time, the IP addresses were allocated quite excessively. And now we're actually running out, and we have actually run out of IP addresses. They've all been allocated. So eventually we will need to move to IPv6, which I'll mention briefly at the end. But for now, there's other technologies in place for us to be able to keep using IPv4, even though we're getting more and more IP addresses and more devices in use on the networks. Now, these are, we have what's called public IP addresses and private IP addresses to deal with this. Okay, so on the internet, just remember that an IP address always has to be unique. Always, always, always. So in order to deal with that, they've allocated a private IP address range that people can use however they wish on your private local network. So if we have a look at this next slide, within each range, we're just going to look at class A, B and C, there's a private IP address range. Now when you do your practicals, they will always come from one of these ranges. So you'll see the class A, anything that starts with a 10 is a private address. And then in class B, anything from 172.16 through to 172.32, those you can use however you wish. And in the class C, you might be familiar with the 192.168 range. Most routers at home come pre-configured with that IP range. Now these private addresses cannot be routed across the internet. They cannot be used publicly at all. They're reserved just for exclusively for local private networks. Now let's have a look at private IP addressing in a network. So here's an example IP address, 192.168.1.1. In order to make this IP address meaningful, you need to give it a subnet mask. And this is where we're going to start explaining what this subnet mask means. So a subnet mask tells us what portion of the IP address is the network ID. Now this is very important. The network ID, you must be able to determine the network ID from an IP address. This is what enables you to be able to configure an IP address for computers. So if we just have a look, I'm just going to briefly look at the binary behind this before we move on to working out your IP addresses in decimal. So this is our IP address 192.168.1.1 in binary. Okay, now let's look at the subnet mask in binary. Our subnet mask, it's got all ones on the left and all zeros on the right. That must be it must be that way. You can't have these ones anywhere in here broken up by a 0, because then it wouldn't work as a subnet mask. So the ones denote the network ID, and the zeros tell you what is the host ID. Now this is important because we have two rules in the network. And rule number 1, the network ID must be the same for all computers on the network. And rule number 2 is the host ID needs to make sure that your IP address becomes unique. You cannot have two IP addresses the same on a network. You get IP address conflicts. Okay, so on these ones tell us what's the network ID, and the zeros tells us what the host ID is. So if we can have a look at this back in decimal up the top here, see the ones are where the 255s are. That means the first 3 octets represents the network ID. So in this case it would be 192.168.1 is our network ID, and the host ID will just be 1. So let's have a look at this, and we're actually going to build a network now and connect computers to it and work out how we can get an IP address. So first we have a switch. We're going to plug our computer into the switch. And using the example before, we're going to give it an IP address. So there's workstation 1, and I'm giving you the IP address 192.168.1.5. And the subnet mask 255.255.255.0. Now, as we worked out before, when we actually worked out the network ID, we converted into binary so we could see, but we don't need to convert into the binary to see the ones. You can just know that the 255's portions is where the network ID is. So now we're going to connect our second computer. So how do we select an IP address so that these two computers can talk to each other? If you just pick any IP address, it will not work. It won't work. So let's work it out. Rule 1 of the network. The network ID must be the same. So, okay, let's work out the network ID. We got 192.168.1.5, and there's our subnet mask. So where the 255s are, I've bolded it and underlined it. That's our network ID. Okay. Rule 2 of the network, the host ID must ensure the IP address is unique. So the host ID has to be different. So let's go back to our little network here. I've just written down the network ID there, 192.168.1 and .0. This is the way we normally write the network ID. Okay, now something else you need to know is that you cannot ever allocate that IP address to a computer. That is the name of the network. It's the ID. It's not a usable IP address. The first IP address is not usable at all. Now, the last IP address is also not usable for a computer. This is a special IP address that's used for broadcasting. A broadcast is where a message is sent out automatically to all computers. So that last IP address also can never be used. That gives us an available IP address range of 192.168.1.1 all the way through to 254. So we can use any IP address from that range for this computer that we've connected to the network. Okay, 5's are obviously already in use. So let's give it another IP address, 192.168.1.6. And as always, we have to give it the subnet mask so we know that it's on the same network. So there you go. We've got two computers that can now talk to each other. Now, as another example, I'm going to throw in another switch. They're not connected at the moment. Total separate network. And I'm going to connect my computer, and it's called Comp1 because it's got nothing to do with this network. And I'm going to use a Class A private address, 10.20.5.6. And now notice my subnet mask has now changed. It's 255.0.0.0. So, if I connected a cable between these two switches, would these computers be able to talk to each other? The answer is no, but let's go and have a look at why. So, remember our rules. Rule 1 of a network, the network ID must be the same. So let's have a look at what the network ID is. Remember that the network ID is determined by the subnet mask. So where the 255 is, that's only in the first octet. So that means the network ID is 10. And we would write that as 10.0.0.0. So that means rule 2 of a network, remember the host ID must make sure that the IP address is unique. So that means that we've got the last 3 octets that we can use and change to give a computer an IP address. So where in the IP address that we had before on the first little network, we only had the last octet that we could change. We've now got 3 octets that we can use for the host ID. So let's have a look at the details. So our network ID, there it is, 10.0.0.0. The broadcast, remember that last IP address you cannot use on it for a computer, 10.255.255.255. And so that gives us available IP addresses that we can allocate to a computer all the way from 10.0.0.1 through to 10.255.255.254. So in the first network, we can only allocate 254 IP addresses. We can now allocate over 16 million IP addresses by using this Class A IP address. Now, these two computers, they can't, the two networks, they can't connect to each other. But the internet, the whole entire internet is made up of lots of different networks with different IP ranges. So how do we get these two networks connected together? And that's where the router comes in. That is all a router does, is it routes from one network to another. Some of you may have a router at home and it connects you to the internet. It also provides other services that you need on the internet, such as DNS for resolving names to IP addresses. It quite often has built-in firewall filtering. Some of it even have USB file sharing, media streaming. They have all these different services built in, and quite often you also have a modem built into them as well. So you'll get an ADSL modem router, and the modem establishes the connection to the ISP, but meanwhile the router component, all it does is routes from your network to your ISP's network. So just remember that distinction and make sure you don't get confused between your home routers, which are completely different to what you actually see in larger networks. Okay, the other key point that we need with this router is each of these connections that it has, there's actually an interface, a network interface, or a NIC. So it needs a NIC for each network it connects to, and it can connect to more than two. Your home router only connects to two. One's your ISP and the other one's your local network. But in enterprise, you can have many NICs in a router. You can keep plugging in extra NICs depending on the type of router you have. And those NICs also need an IP address. So for each network it connects to, we have to allocate an IP address. So if we have a look, okay, 192.168.1.1 for one NIC. Now that is on the same network as the computers on the left network. Okay, and we also need to give the other NIC an IP address which will connect to comp1. So there we have it. I've chosen 10.0.0.1, but it can be anything within the range that we worked out down here. Okay, now for each computer to connect or to be able to send data to the computer on the other network, they need one more thing that in their configuration. It needs to know where to send packets of data that it doesn't know where they're supposed to go. So if a computer is connected on its own switch here, so workstation 1 can send data to workstation 2 via the switch, and the switch can direct that traffic. But if workstation 1 wants to send a packet to comp01, it needs to know where to send because it doesn't know anything about this network. And the router is the one that knows where to forward traffic to. On the computer, this is known as the gateway. So every computer needs to be configured with a gateway address. It's like the door out of your room. Say you've got a room that has just one door, your bedroom. You need to know where that door is to be able to exit your room. And it's the same thing with the computer. So for workstation 1 and workstation 2, this IP address up here for the router 192.168.1.1 will be its gateway. And for comp1, its gateway will be 10.0.0.1. So if we just fill in those gateway IP addresses onto a computer, and now they will all be able to talk to each other. So let's explain a little bit more about the subnet masks. So as I said before, the subnet mask tells you which portion of the IP address is the network ID. Now there's some default subnet masks for each class range. So for class A, the default is 255.0.0.0, and as you can see, class B, the subnet mask means the network ID is the first 2 octets, and for class C, the subnet mask will be the first 3 octets. And you can see that for each class range, the number of networks that you get plus the number of the computers that you can have on each network changes. So for a class A, you don't have very many networks, but you can have over 16 million computers. But for a class C, we've got 2 million networks, but only 254 computers per network. So class C means you can have lots and lots and lots of small networks, and a class A means you don't have very many networks, but they're very, very big ones. These can change. These are just the default subnet masks. You can change them, okay? So just remember these aren't fixed, and that's important because when you work out the network ID, don't just go on what you remember as the defaults. You need to be able to read the subnet mask and determine the network ID. So let's have a little practice at that, working out the network ID. So in example 1, we've got an IP address 153.92.100.10. And the subnet mask is 255.255.0.0. So in this case, we're going to work out the network ID. We can see that 255.255 is in the first 2 octets. So that means for our IP address, the first 2 octets is going to be the network ID. So this gives us 153.92.0.0. And likewise, where the zeros are in the subnet mask, that's the last 2 octets. So our host ID will be 100.10. Now for example 2, I'm going to let you work this one out, and you can answer this question in your quiz that you get to go with this video. So you can calculate this one, and as you can see, the subnet mask is changed. The IP address is the same, but the subnet mask is now different. Okay, going on to CIDR notation. This is known as classless interdomain routing. This is just an abbreviated way of actually writing out an IP address and its subnet mask. So if we have an IP address 192.168.1.1 and the subnet mask is 255.255.255.0, this is a long way of writing out the IP address. Now let's have a look at the binary again just for a moment for the subnet mask. There's 8 ones, dot, followed by another 8 ones, followed by a dot, followed by another 8 ones. And if you add all of these up, that gives you 24 ones. Okay. We can, instead of writing out this whole subnet mask, what we can do is write 192.168.1.1/24. And as you get familiar with writing these IP addresses and working out the network ID, you'll know off the top of your head that if you see subnet mask with 3 octets, that's going to be 24 ones. Likewise, if you had a subnet mask 255.0.0.0, there will be just 8 ones because it's just the first octet. So this is just so you're familiar, just so you know, this is a shorthand way of writing the IP address with its subnet mask. So here's an example of subnetting and supernetting. Remember how I said that the default subnet masks do not have to stay the same? You can change them. Now, you don't need to know how to do this unless you go on to Cert 3. In Cert 3, you'll have to have a go at subnetting and supernetting. But just for Cert 2, you just need to know that it's there and that it can be done. You don't have to calculate it yourself. So what we have here now is we no longer have a subnet mask where the ones are completely within an octet. We're breaking it up in the middle of an octet. And the thing I want you to know here is that, as a reminder, you cannot put ones in the middle of your subnet mask here. Okay, you always have ones on the left and zeros on the right. And the more zeros you have on the right, the larger your network will be. Okay, whereas the less zeros you have on the right, the smaller your network will be. So if we add in a 1, which is called a bit, this is known as bit stuffing. Okay, you put in enough bits that you need for the size of your network. And if you have a look here, by doing this, we have a finite amount of subnet masks that we can actually use. So because we only ever have the ones on the left and the zeros on the right, that gives us this graph, these exact numbers that can only ever be used in a subnet mask. IPv6. So just to touch briefly, IPv6 gives us a lot more IP addresses. It solves a lot of the problems in IPv4. We haven't moved to IPv6 yet because extra hardware is required to maintain both the IPv4 network and the IPv6 network until the transition is complete. A lot of organisations are not able to do that, or it's cost prohibitive. But eventually we will need to switch over to IPv6. So IPv6 gives us a lot more IP addresses. It's a 128-bit IP address as opposed to the 32-bit of IPv4. It adds in security. It reduces the need to have subnet masks. Actually, it eliminates the need for a subnet mask, and it has built-in quality of service. As I said, an IPv6 address is 128 bits, and it looks a bit like this. Okay, so it's using a hexadecimal format, and that allows us to have a much larger range of IP addresses. In fact, there's more IPv6 addresses than there are observable stars in the universe. So that's quite significant. We won't run out of IPv6 addresses anytime soon. So just as a summary, an IP address is required to allow computers to connect between or to talk to each other on a network. Okay, an IPv4 address has 4 octets, and the computer translates these into binary. Just remember that they're divided. The IPv4 addresses are divided into 5 class ranges, but you can only use A, B, and C for actually on your network, and you have a private range that you can use for your local computers. The main 2 rules you need to remember, and this is pretty much core to this entire unit: the network ID has to be the same, and the host ID must make your IP address unique. Without that, you cannot have computers successfully talking on the network. The subnet mask is the part that helps you calculate the network ID. That's and the CIDR notation is the abbreviated way of writing the IP address and the subnet mask. We didn't go into supernetting and subnetting, but just remember it's a way of breaking up larger networks or joining together smaller networks. So it's going away from the default subnet mask that you get with the class A, B and C ranges. But none of this will be necessary when we move to IPv6. So that's it for this talk on IPv4. Some of this can be a little bit technical, and if it is challenging, make sure you have a talk to a lecturer if there's anything you're struggling to understand. Try re-watch the video as well to see if there's anything new you can pick up. Thank you for watching.